The topic of this video will be on how to perform a general linear least squares regression. This is after 3.11 of Wessel. So far we've covered simple regression. And that involved fitting X and Y, our data pairs, to a line. The function we were using was a line. So our model function, I'll refer to that as y sub m, was equal to a1 plus a2 times x minus x0, or each, I should say, right. So that would describe our line function that we fit, and we learned how to do that. We could just as well fit our data to another function. Say a parabola, or any polynomial for that matter. And I'll write that model equation as a1 plus a2x plus a3x squared all the way up to am x raised to the m power. And in this example, I've just set the reference value of x, which is x0 in our simple regression, to 0. So you can see that this is a polynomial which could do as well or better job, perhaps in some cases, of fitting our data for y as a function of x. We could also fit it to a periodic functions. Okay, so there are many cases in which y will be a periodic function of x, where periodic functions may be the more appropriate functions to try to fit and describe our data. In general, and this is why we're calling this general least square regression, we can describe our model as a sum of functions of x with coefficients corresponding to those functions. So our functions are what we'll refer to as our basis functions. Let's see. So this is f sub k will be the kth basis functions. And the a's are the coefficients. And they describe simply how important a given function is to the overall fit, right? So the bigger a is, the more substantial this function has in describing the model. So this is the general form of the model we're going to try to find for our data pair. And just to take a step back and look at the big picture, so the statement of the problem can be written as such. For n measured pairs, or n measurements of x and y, the problem is to solve for the coefficients again, we'll use the symbol A for m basis functions that minimize the sum of square misfit between the model and the measured value of y. Okay, so that's a summary of the problem. And I'm going to go ahead and write down the answer, the solution. And I'd like to do so just to show you that it's a relatively simple solution. So if our vector of coefficients is x, again, that's what we're seeking to solve for. The answer is that those coefficients are equal to an equation, a matrix equation written as A transpose A, and the inverse of the product of that matrix multiplication times A transpose times B, vector B, and that's our vector of y's. Okay, so we've stated the problem, I've given you the answer, and so now I'd like to go through and show you how this answer comes about. To begin, let's write out an equation describing the sum of square misfits. We recall that we called that capital E, and that's the sum over all values of x, the error between our model and our measured value of y squared. And we can write that out using our equation for our regression, our general regression, as the first coefficient times the first function evaluated at each measured value of x, plus the second coefficient times the second function evaluated at point xi, summed all the way to the last coefficient times the last basis function evaluated at point xi, and then we have to subtract our measured values of y and square it. So again, this is the function f1 evaluated at each point of x. And let me write this in a slightly different way, in a way that Wessel actually writes it. Instead of the, so I'm just going to abbreviate what I've written here, is f1 evaluated at point I, A2 times f2 evaluated at point I, all the way to the mth basis function evaluated at point I. And just to be sure we're all on the same page, this part describes the model value of y, and we wrote that as y sub m for all values of x, and this is of course the observed values. And we're eventually going to want to write out an equation describing E, and again, as I talked about in the last video, or in one of the earlier videos, E, capital E, is equal to E transpose times E, the transpose of the error vector times the error vector. So let's write out the error vector. So the first component, E1, is of course, and I'm going to switch the order in which I write the F. So that's F11 times A1 plus F12 times A2. I'm just rewriting what I wrote before more explicitly for the first value of the error. Likewise for the second, that's F21A1 plus F22A2 plus all the way up to F2MAM all the way down to the nth error, which is equal to Fn1A1 plus Fn2A2 FnmAm. And we can write this in vector form as a vector equation or matrix equation. So our left-hand side is our error vector. Again, we have n errors for each measured value of x, well, each point of x measured, and each point of x and each value of y. And the f's become a matrix, again, of these different functions evaluated at these different locations. And then we have our coefficient vector. And in general, we'll have m coefficients. And that's all minus our y's. And I'm just noticing that I forgot to write the y's in the above equations because we have to subtract from our model, which is the function, which is our sum of basis functions minus our measured value at 0.1 and so forth. Okay. Okay. All right, so this is the equation right now. Longhand, this is the vector equation or matrix equation written out. And this is vector E. The left-hand side is vector E. We'll call the matrix A, and our coefficient vector X, and our vector of y values B. So we have E equals A times X minus B. So this is our equation describing our error. And just to make sure we know that this is a column vector with n rows and one column. This is a matrix with n rows and n columns, and X is a column vector with m rows and 1 column, and finally we have a matrix that's n by 1. So we can confirm that we can do this, carry out this multiplication because the inside dimensions match, and the product of A and X gives an n by 1 vector. And I'd like to point out that the jth column of A gives the values of the jth basis function for all n values of X. So each row of the A matrix gives the value of a single function for all values of X, and each row of the A matrix gives the values of all the functions at a given value of X. So again, the matrix equation describing our errors is our error vector is equal to A times X minus B. Now let's look at the sum of square errors. And the matrix equation describing that is E is equal to E little e transpose times E. And by substituting this expression in for little e, we get AX minus B transpose times AX minus B. And that we can apply some matrix algebra, linear algebra, so to speak, and that becomes X transpose AX. So that's the product of the first two terms in the parentheses minus the first term in the left parentheses times the second term and that's X transpose A transpose B. And then we take the second term in the right-hand parentheses times the first term in the second term in the left-hand parentheses times the first term in the right, and that gives B transpose A times X. And then finally we take the product of the two right-hand terms, and that gives B transpose B. So I hope you're starting to see some of the power of linear algebra. It would be quite well, it'd just take a bit more paper to write all of these out. Now the next question I'd like to ask you is, does the sum of all these products lead to a scalar, vector, or a matrix quantity? And why don't you think about that, stop the video, and come back with your answer. Well, the answer is it's a scalar. We simply took each of our errors, squared it, and summed it, and that's a scalar quantity. And one easy way to see that is, remember, B is a vector that is the transpose of which is 1 by n, and we're multiplying it by b, which is n by 1. So the resulting vector is 1 by 1, or the resulting quantity is 1 by 1. So that's a scalar quantity. If we look at this term, we have a 1 by m vector, that's x transpose. A transpose is an m by n vector. A is an n by m vector. And x is a m by 1 vector. So again, the inside dimensions match, so we can carry out those products. And what's left is 1 by 1, the two outer dimensions. Now, if you'll recall, the problem is to find the coefficients that minimize the sum of square errors, or sum of square misfits between the model and y. Okay, so this gives our sum of square misfits for any value of coefficients. We'd like to minimize it. And to minimize it, we need to, to minimize, E with respect to, for example, the first coefficient, we're going to need to take the derivative of E with respect to A1 and set that equal to 0 and solve, well, and solve for A1. But I'm going to leave that towards the end, And we need to take the derivative with respect to A2 and set that equal to 0, all the way down to the derivative with respect to AM, set equal to 0. So we're going to have M equations, and we're going to solve for M unknown coefficients. Okay, so this is how we're going to solve our problem. And before doing that, I'd like you to notice that we can describe a vector of derivatives. We can describe each of these terms as a vector. Use a different color. And this is going to be a vector which we'll call the derivative of E with respect to vector A. So this is a vector of partial derivatives. And the vector involves M partial derivatives, so it has a length of M. So I think I'd like to wrap this video up, this first half of the video right now. Again, our problem is, given our measurements of x and y, we want to solve for the m coefficients for the m basis functions that minimize the sum of square misfits between the model and each value of y. And our sum of square misfits is described by this matrix equation, and we're going to minimize that by taking the derivative with respect to each of our coefficients and set those equal to 0. So we are left with m equations to solve for m unknown coefficients. And in the next video, I'll complete the solution to the problem.